So our next speaker is Professor Larry Ukeiley, who's currently a professor at the University of Florida. He has earned his PhD from Clarkson in 1995 and has done has had a couple of research positions both at the NASA Langley Research Center and also at the University of Mississippi. I think it was acoustics or something like that. Sorry. So Professor Larry Ukeiley, who will be getting us onto the detailed techniques, starting off with proper orthogonal decomposition.
Okay, so Tim sort of set it up really well in terms of the different techniques. Obviously, based on what he said, the proper orthogonal decomposition is going to be a data-driven technique. So it's a technique, I'll talk a little bit about extensions where people have tried to not use it as a data-driven technique, but it really is based on the data. So just to give you a little bit of overview, I'll give a little bit of an introduction. And for lack of a better word, I've taken some of the notation that's out there in the current literature and calling POD based on what Lumley proposed in 1967 as a classical POD. Then talk a little bit about the Snapshot POD, which was a derivation of it or an adaptation to it in order to help deal with large data sets by Surovich. Then I'll talk about early applications. Talk a little bit about universality of modes and how we might be able to extend some of the modes, and that'll be an application from some of my data to cavity flow. And then finally, I'll talk a little bit about some of the flow properties and going back to exactly where Tim started and making sure that you take care of symmetries, homogeneity, stationarity, and all those properties in the flow field before you apply these techniques, because the results can be a little bit deceiving if you don't. So the proper orthogonal decomposition, at least in the context of turbulence, was introduced by Lumley in '67. And really it came at a time, so like I said in the introduction, I'm going to be doing more of a historical perspective on this. It came at the time when we were just starting to understand about this underlying coherent structure buried in the turbulence, right? When you look at the literature in the 50s and 60s, there was still this notion of everything being small scale, not this underlying large scale motion that as we know now, tends to govern at least the large scale, the larger part of the dynamics. So really what he wanted to do was to develop a way to pull out this embedded structure in a turbulent flow field. And at the time, and if you look through the literature in the 60s, 70s, and even into the 80s, there's just a slew of coherent structure reduction techniques. Many of them are empirical, many of them are ad hoc, but what he wanted was one that was mathematical. And the reason why we wanted this mode was exactly what Tim was talking about. The ability to pull out a mathematical mode that I can then use to develop some type of model for the flow field. And if I just have a picture of a model, I obviously can't get anything analytical. So the goal was to pull out something mathematical, okay? So this is actually cut and paste right from the Berkouze, Holm, and Lumley, the annual review article. And basically there's 3 points, right? So what we want is something statistically based, and we need to be able to extract it from experiments and simulations. I'm going to lean probably more towards experiments. That's where my data and my background comes from. It has to be analytical and supply clear understandings of its limitations and capabilities. Meaning that when we look at the problem that we're going to solve to extract out the POD modes or the proper orthogonal decomposition modes, there's some limits to that integration that we're going to actually have and that projection that we're going to go through. And one has to understand them. Okay, and finally, what we really want is something that can have our ability to bring out both the spatial and the temporal modes of the flow field. And we have to think about these spatial and temporal modes combined, okay? So it's not going to be this separation of variables necessarily that we tend to, at least modernly, tend to think about POD. We have to go back to that integral and actually treat it as a four-dimensional space that we need to look at. Okay, so when we look at the major uses, obviously based on the history, the first use of this was really to pull out coherent structures, really to get an underlying picture of what some of the dominant features in turbulence are. And when we talk about the projections, we'll start the same place where Tim was talking about in terms of kinetic energy, because that's tend to what we think about the turbulent flow field. So from a fundamental perspective, if we can pull out something that represents the maximum amount of turbulent kinetic energy, the rest of the flow hopefully will follow. Obviously, when we start to look at dynamical systems and control, that's not necessarily what we're looking for when we're looking for control. When we're trying to extract the underlying physics of the turbulence, it's a little bit of a different question there. So that's where some of these extensions that we're going to talk about today, especially the balanced POD, I think Clancy talks about observable POD and all these other extensions to it, are based on the dynamical systems approach, not necessarily trying to get at the root of what the underlying physics of the turbulence is. So there's a little bit of a disconnect, let's say, between where it was initially came from and where it's going in more recent times. Okay, so obviously I'm going to be citing references in here. I said it's historical. It's also a little bit of a Homer type presentation, so I'm going to be doing stuff mostly from my group, or actually my academic line, so from Mark Glauser and all these other people. So I just pulled out this plot from Joel's thesis, because I did part of my PhD in Poitiers with him at that point in time. So this is a plot of the amount of publications with POD, right? So it might be hard to read because it was scanned in. But when you look at when it came out, it was in the late 60s, so 2 or 3. By the time it was, oops, what's that doing? Okay, maybe we'll go with the pointer. So by the time we reached the 90s, there was about 60 publications with POD in it, or talking about POD. So I pulled this out from Google the other day. So when I look at, for example, 2015, 1,100 papers. And this is just, mind you, this is just POD in the title. So that's not even going to consider all the papers that are talking about POD that don't actually include it in the title. So it really has turned into something that's ubiquitous in our trying to understand fluid dynamics or turbulent flows. And I have to be a little bit careful with saying turbulent flows, because it's definitely applied to a lot of transitional flows. It's applied to some low Reynolds number flows that really aren't turbulent. And so it's just a technique that's been there. So before I go any further, I'm going to apologize, because I'm sure there's a lot of people in this room that have written papers on POD, and they definitely won't be cited in here. As I said, I'm going to be a little bit of a homer. And so I'll just go with what I want and do that. So as Tim said, there's lots of extensions. So he mentioned the extended POD, there's the double POD, there's the balanced POD, there's the spectral POD, which is not quite sure, that's not what we originally started with, but we'll show that a little bit in a little bit. But there's lots of techniques, and I'm just going to stick with the classical POD as I go through this. Okay, so the basic premise that we have here is that I'm going to take some deterministic structure, which we're going to call phi, and it's going to be a vector, so it's phi, and this is going to be something that's a function of space and time. I'm going to end up projecting that onto my random field, which is ui, my velocity field is a function of x and t, and I'm going to try and maximize that projection. And I'm going to do it in a mean square sense such that alpha squared is going to be maximized. So when I go through the mathematics of that, I'm going to end up with this integral eigenvalue problem that I have right in the middle here. Okay, so this integral eigenvalue problem, when we start with this, is going to be in 4 space dimension, right? So it's going to be over all my spatial dimensions as well as time. So when I look at that, I'm going to end up developing this 2-point correlation tensor, which is going to be a function of xx prime, tt prime. So x is my spatial vector, t is my time, temporal vector, or temporal information, and I can build up this cross-correlation tensor from that. So when I look at the solution to this integral eigenvalue problem there, what I'm going to pull out is I'm going to pull out eigenvectors, which are basically, if you want to say, some type of typical organization of the flow, or the organization in the flow, which is going to maximize whatever I'm using in my projection up here, right? So in terms of the mean square, if I read it in terms of velocity, it's going to end up maximizing the turbulent kinetic energy, because that's what I've written here. I should point out that we're going to always, or at least in what I'm going to talk about, we're going to be applying this to only the fluctuating field. So I've already done a Reynolds decomposition, and I've pulled out my fluctuations away from my mean, and I'm just trying to extract out the turbulent structure that we go there. The eigenvalue here is going to represent the energy. So this is my weight of how important this mode is, and in this case, at least in terms of the turbulent kinetic energy. Okay, so due to the properties of the kernel, as Tim introduced a little bit before, the fact that I have this kernel, my 2-point correlations, being a positive definite matrix, when I actually look at what's going to happen, my solutions are going to be governed by the Hilbert-Schmidt theory, which allows me to, first of all, discretize. So now I'm going to say I'm going to be able to come up with n modes from the application of the proper orthogonal decomposition, and these modes are going to be, at least in this case, energy weighted. Okay, so my first mode is going to be the most amount of turbulent kinetic energy I can have, and so forth as I go down. I probably should have normalized the projection when I did before, but when I look at that, that's going to give me a set of orthonormal modes that I have there. And then the other thing that it's going to allow me to do is to actually take my velocity vector that I started with, or my velocity field over here, and I'm going to decompose it in terms of this expansion coefficient times this basis set, okay? And when I've done it here, this expansion coefficient, the basis set has all my space and time. The problem with some of this is that when I actually look at this, in order to determine that expansion coefficient, I'm going to have to solve this integral, okay? So that means that in order to be able to solve this integral, I have to know my full field information about my velocity vector. So going back to the historical perspective, before we had PIV, or before we had large-scale simulations, this integral was impossible to solve, right? We only had slices of the flow field, and we actually had to build things up statistically. And as we learned from that, I think there's a lot to learn as we go along through that. So that's why I'm going to do a little bit of the history. Okay, so I can, again, reconstruct my correlation, which is the kernel of that integral eigenvalue problem I have, as just my eigenvalue times the square of my eigenfunctions, depending upon which domain I'm in. That might be a complex conjugate. Here it shouldn't be, but it is, regardless. And then I can actually look at, again, as I said before, these eigenvalues are going to be positive based on the fact that the kernel that I had was a positive definite matrix. Okay, so here's where we have to be careful. We have to be careful about the domain which we're applying the POD. And this comes from, or at least a lot of what I've pulled out comes from a recent paper by Bill George, sort of trying to hammer this home again. So we have to be careful about stationary and periodic and homogeneous directions in the flow field. When I go back to that domain, when I did that original projection, the problem with that original projection is my bounds on that integral. Okay, and that bounds on those integrals have to be over a finite energy. So if I have directions in the flow which are infinite energy, when we think about periodic directions or something like that, I'll try and stand still, it has infinite energy. So what happens when we actually look at that, the bounds on that integral from the original POD or that original eigenvalue problem are not satisfied, so we have to make sure that we actually do something to handle that. And the way we do that is we actually use, as Tim said, we use Fourier decompositions, because those are the way we handle periodic and stationary directions. So for example, if we have a flow that's stationary in time, which I'm an experimentalist, so in my wind tunnel, everything is stationary in time, so that's always where we start. I'm going to need to Fourier transform that in time and work with my POD modes in spectral space. Okay, so again, when we actually look at that, to actually solve this integral proper over the right domains, we need to be in the Fourier domain. Okay, if we start to look at other flows, and whether this be the axisymmetric jet, which I'll use an example of, Stas has done stuff with a planar wall jet, not a planar wall jet, a planar jet. I've done stuff with a two-dimensional mixing layer. In that case, what we're going to have to do is we're going to have to take that periodic or that homogeneous direction in the span, and we're going to have to do a wave number decomposition in that direction. Okay, so we need to make sure that when we actually look at what we're doing with the POD, we're only applying that POD integral over the strictly non-homogeneous directions which have the context of the finite bounds on them. I played with the order of the talk about 20 times up until about a half hour before the talk. And I wasn't sure when to introduce the snapshot pod, but I'm gonna do it right now. And this comes about in about 1987 from Surovich. And if you think about what was happening in 1987, right, we were starting the numerical simulations, Moyne and Moser's simulation of the turbulent channel flow, PIV, all these other techniques were becoming, experimental and numerical techniques were becoming very prevalent. So if I go back to, well, I can go back to here, when I actually look at this integral, I'm going to have Rij as my kernel, okay, and that's a function of x and x prime. So if I have a large spatial domain, x and x prime, when I correlate every point with each other point, that matrix starts to become huge. Okay, and especially if we think about a three-dimensional flow or even a two-dimensional PIV, that matrix starts to become huge, and then we have problems solving that eigenvalue problem. So basically what Surovich was able to do was to recast the problem. Okay, and he was able to recast the problem by switching the summation in terms of space and time, and then he was going to use what's called a snapshot methodology. So if we go back and we look at that, I'm going to try and get my POD modes here, and we're just talking now about spatial modes, and we're going to say that they're going to equal to this linear combination of the summation of my instantaneous velocity field, which is at some snapshot t, times this intermediate eigenvalue. Excuse me, this intermediate eigenfunction. Okay, and where that intermediate eigenfunction comes from the solution of the eigenvalues of this matrix right down here. So what that allows us to do now, when I look at what I'm doing here, you can see that now my matrix is tk times tl. Okay, so the matrix that I'm solving now is now a number of my snapshots, not necessarily a number of my spatial domain. So if I look at numerical simulations or if I look at high resolution PIV, it's going to end up being a smaller matrix or a tractable matrix that I can actually solve. There's some issues about whether that is the same answer. Okay, and it has to deal with the fact of whether the flow is stationary or not. If you look at Surovich's original paper, when you go back and you plug it and you redo the math of trying to get what these snapshot modes are, because of the way we're defining the two-point spatial technique, first of all, each of your snapshots are supposed to be statistically independent in order to build up that ensemble average. Okay, when you think about what people typically apply this to numerical flow or stuff of that nature, they're not. So there's some issue, but we can assume ergodicity and say that a temporal average is the same as a spatial ensemble average, and we could probably wipe that under. The other thing is that the summation also assumes that this temporal stationarity. Okay, and if we think about the temporal stationarity, going back to the original POD integral eigenvalue problem that we're solving, that implies that we should have actually used Fourier modes in that, not necessarily doing this. So while the snapshot POD and the applications of it yield interesting results, it's not always clear to me and other people whether that when I actually go back and I try and get these modes, these are the exact same modes I would have gotten had I applied the classical POD. Okay, and we can show that. There's several examples where we can show that. I should point out some other work by Nadine Aubrey and some other people where she actually tried to do this splitting separation of variables and where they had what she called chronos and tempos and topos and was able to try and do the separation of space and time. Okay, so again, early applications. Let me keep going here. So the original application was 1967. Again, remember, this was Lumley trying to come up with a definition, a mathematical definition of basically Townsend's large eddy. So he took Grant's data and was able to actually extract information from some of the correlation data and was able to actually pull out these counter-rotating vortices as the large-scale data. But again, remember, this is the late 60s. The data that were driven by was hot wires. Okay, so the data was extremely sparse. Bakewell and Lumley again did something where they were trying to look at the large-scale structures in the near wall of the pipe. And basically, if you follow Lumley's, it was 67 was Bakewell and Lumley. Herzog was hired in to do those experiments and spent 10, 15 years. That was always the joke in our group of having less than one for your Ziggy number in terms of graduation because he was a PhD student for a heck of a long time doing these experiments. He really never published it. Nadine came along, Aubrey came along, and actually used the data from Herzog to actually develop this dynamical systems model, right? So this is really where the start and the blossoming of the POD happened. If you go back to that chart originally from Delville, about the late 80s is really when everybody started to see the power of what we can extract from this, and she was able to basically develop a dynamical systems model for the large-scale structures of how some of the phenomena near the wall. The Moyne and Moser work in the late 80s, which from a coherent structure perspective, that was the simulation, right? If you go through your literature, that is the simulation that every coherent structure technique was developed on. All stochastic estimation and all these other stuff was born out of that. But in Moyne and Moser's paper, they pulled out these counter-rotating structures that were down in the wall. If we go a little bit further along, and this was probably one of the first major applications of the Snapshot POD, was Remfer and Fosel doing a transitional boundary layer study. And again, what's interesting is that when they did this, they actually still took into the accounts the homogeneity in the flow field. So when they pull out these modes, they were actually in spectral space. I should also point out that Moyne and Moser do a beautiful job of explaining the similarities in that flow and what we should expect in some of the correlations. So now being a little bit more selective to my group with free shear flows. Okay, so some of the early applications were the axisymmetric jet from Mark Glauser's work, and unfortunately I don't have a picture of his hot wire rakes, but basically we had he had an axisymmetric jet and then built up a correlation. So basically he was able to build up the correlations such that he could solve this eigenvalue problem. So again, what he was looking at is this decomposed in the Fourier direction, in the frequency direction, so time, in the azimuthal direction around there, and then really strictly only applying the POD over the non-homogeneous direction, the radial direction. And when we look at what he gets his eigenvalues, which are now a function of theta on this axis, frequency on that axis. So when we actually look at this, and this picture is hard to look at because it looks inverted, what we see is we see two peaks in the dominant eigenvalue spectra. We see one associated with a frequency that's around a Struve number of 0.2, 0.3, which is what we would expect with the jet. And we see a dominant azimuthal mode number associated with about m equals 6. Okay, this was done at an x over d equals 3, so it was pretty far up in the jet. It was before it settled into probably what we expect all these jets to settle into, which is an azimuthal mode 1 or 2 as we go further downstream. But it was able to actually, looking at the way the energy transposed through this eigenvalue spectra in my theta frequency domain, able to come up with a model of how the ring structure in the jet would evolve. This is work done by Delville et al. in Poitiers. And again, taking that similar analogy, but looking at a two-dimensional mixing layer. And again, when we think about what it was doing, solving it in this direction, or in this methodology, was necessary. Okay, and it was necessary because all we had was linear arrays of data. We never had a full plane of what the data looked like in that direction. So I had to build this up statistically anyway. So inherently, we had to solve the POD problem in this manner in order to get the data set, versus what we don't necessarily anymore. So we could actually build this up, and this is a study by Sorovich's group with Rajay and Carlson, and they were able to build the whole thing up with 2 probes. Okay, so they were able to build up the whole statistical 2-point correlation with 2 probes. So think about the tediousness of that. Everybody that now wants to just hit the button and walk away from everything. Okay, so problems with this. It's a data-driven technique, right? So when we think about that, that means we have to think about spatial resolution, right? At some point in time, we're not going to have the resolution to actually resolve the flow field or the modes are going to truncate off. You can think about it almost like a spatial aliasing type phenomena going through there. Wow. Okay, so I guess I got to pick up. So what we can see there is we can see that when we look at this, there's this concept of a 2n plus 1. So if I look at my eigenvalue spectra, I can start to see it dropping off, and I can start to look at some of the domain that's important there. The other thing about data-driven techniques is that we have to think about the data that we're using. Okay, so these are eigenspectra. So again, this is the two-dimensional mixing layer. And what Joel did in this work was he first applied the POD to just U, then UV, UW, and so forth. And one of the things you can see when you look at these eigenspectra, you can see is that you get different information. Okay, so one has to be very careful about the information that you're using in your kernel, because you might get different peaks in the flow field associated with what the dominant eigenspectra would be. So obviously, experimentalists, we don't have all the information like a numericist does, and so we have to be able to decipher what information we're using in there. We could look at what the norm is, right? So everything I've talked to up this point has been with a TKE norm. There's no reason we can't actually look at entropy and look at the mean square vorticity field. So probably the first application I ever saw of this was Moser in 1988. But this work by Costas, which is with Julio Soria, which is one of the more thorough ones where I've looked at, where they're actually looking at extracting the entropy modes, and so basically vorticity, versus doing the TKE and then calculating vorticity from that. And what you can see from that is, this is sort of blurry picture scanned from his paper, but regardless, as you can see that you get different information. So again, if you're trying to pull out the physics of what some of the vorticity field might be, perhaps you should use an entropy norm instead of a TKE norm, because that's going to be the dominant structure. The problem once you start to look at this, and if you wanted to actually look at the equations associated with this, if you look at the vorticity dynamics equations, you still have velocity in there, so you have to be careful about when you do the projection. So I just want to do 2 quick examples of some of the stuff that we've done in my group. So this is a cavity flow, and one of the things that one wants to be careful about is, right, so this is empirical data, so one wants to know about the applications associated with it, or the validity of the modes beyond where they're extracted from, okay? And this is important if we're trying to make models. So basically we ran over 4 Mach numbers, or actually 5 Mach numbers. The point here is to show that the mean velocity field, which are what the color contours represent in the background, the streamlines are white, but they're different for all these different flow fields depending on the Mach number that we have there. If I look at the TKE, that's a little bit more similar. Okay, so what we did is we applied a version of the Snapshot POD to this, and when we look at that, we can start to see that when we do the Snapshot POD, because inherently we're applying the POD over the streamwise direction, as well as the strictly non-homogeneous direction, we get very low energy modes, typically on the order of about this somewhere between 10 to 15%. But again, when we actually look at what the modes look like, this was the interesting thing. So for those that know cavity flows, it's driven by this streamwise mode or oscillator mode. But when we actually look at what's happening here, we can actually see some universality in the modes. So if we look at mode 1, at least for the cases of Mach 0.2, 0.3, 0.4, and 0.6, we can see quite similar results. And we can actually go up to about a mode 6, 4 is plotted there, mode 6, where we actually see similarity. So I can actually look at that in terms of, that was pictorially, I can look at it quantitatively, and I can start to see the picture that we can get here, so I can check the orthogonality. So that means if I have a value of 1, which is a red box on the diagonal, that means that the modes are effectively the same from these 2 applications. So we can start to see that, at least when we look at this, there are some commonality of the modes, which might mean if we take this and we try and develop a dynamical systems model, we might be able to use the velocity field or the POD modes from a single Mach number and be able to extend that beyond that capability. Okay, so the last thing I want to talk about in 1 minute is I just want to show this one plot, okay? And what this one plot is this association of doing the POD in the jet. So we can do it in this direction, we can take a snapshot of that, and then we can do the snapshot POD in the XY coordinates, okay? And that's what we see over there, these first couple modes. And this is the problem without taking into the fact that the axisymmetric jet has this periodic direction in that direction. So what the snapshot POD does is it sort of splits up the modes in some arbitrary way, whereas if I sum modes 2, 3, and 4, I actually get what I would expect from my dominant azimuthal mode number. So I liken this to Clancy's talk where he talks about the observable POD modes, and this is from Jeremy Pignet's thesis that he did with Mark, where if you look at it, it might not, if you look at the modes that are ordered from Snapshot, the ranking of them could be very different and very confusing in there. But if you take and you actually do the azimuthal decomposition first, what you pull out is going to be physical. Okay, so one has to be careful about applying it arbitrarily, and I'll leave it at that because I know Doug and Sam are grimacing. So thank you.